Are you ready to explore Fermat's little theorem? Because I am. So let's go. Well, what is Fermat's little theorem? It essentially says if you have some integer a where p does not divide a, then when you raise a to the power of p minus 1, it is congruent to 1 mod p, and that is so useful for reduction modulo primes. And you might ask, why can't p divide a? Well, if p did divide a, then a would be a multiple of p, and therefore when you raise a to the p minus 1, that value, a to the p minus 1, is still a multiple of p, and any integer multiple of p is congruent to 0 mod p, and so therefore it's congruent to 0 if p divides a, and otherwise is congruent to 1. Now we won't go into it this video, but there is a generalization of this theorem called Euler's theorem, and it essentially says that if you have any modulus n, and you raise an integer a that is coprime to n to the power of phi of n, then it is congruent to 1 mod n. And phi of n is the number of positive integers less than n that are coprime to n. And as you can see, if you put in a prime p into this formula, it will yield Fermat's little theorem. Now, in mathematics, it's always good to see some examples to convince yourself it is true and see the theorem in a practical application. Well, let's take 2 to the 4th mod 5. We see that 5 is prime, 5 does not divide 2, and 4 is equal to 5 minus 1. And so, the conditions of Fermat's little theorem are satisfied, and therefore this should be congruent to 1 modulo 5. And as we see, 2 to the 4th is equivalent to 16 is equivalent to 1 mod 5. Now, just if you didn't believe that, let's do a huge example. 7 to the 18th modulo of 19. All the conditions are satisfied, so this should be congruent to 1. And as we see, if you want to verify, you can, but it is congruent to 1. So I hope you're convinced, but if not, the best way to convince yourself is to prove it. Okay, let's get into it and prove Fermat's little theorem. Okay, so it might seem random, but we're going to write down a set of integers from 1 to p minus 1. And what we're going to do is we're going to separate them into separate boxes. And these boxes are going to represent congruence classes modulo p. And the reason we're doing that is because each element in this set is not congruent to any other element in the set modulo p. So essentially they're all different in terms of congruence modulo p. We're going to do a similar thing. We're going to create a new list of all the multiples of a from 1 times a to p minus 1 times a. And we are choosing a such that p does not divide a. And again, we're going to separate them into different boxes. And it's not necessarily clear why we're doing this time because we don't know if each element is distinct modulo p. But that is what we're going to prove very soon. So now these are the main 2 sets we're going to work with for the proof of Fermat's little theorem. Okay, so now we're going to prove the elements in each set are distinct. Okay, so a lot was written down. Let me explain. First of all, we are choosing integers I and j that are greater than or equal to 1 and less than p. And notice how those are the exact integers in the right set. For example, the right set consists of integers 1, 2, 3 up to p minus 1. And those are integers that are greater than or equal to 1 and less than p. Okay, so what does the first statement say? Well, it says if I is congruent to j mod p, which essentially means if element in the right set is congruent to an element in the right set, then I is equal to j, so those two elements are equal to each other. And what does this imply? Well, it means if any two elements are congruent, then they are the same element, proving that all the elements in the right set are distinct, because the only way two elements in that set can be congruent is if they're the same element. So you can't have two distinct elements being congruent modulo p. Okay, what does the second statement say? Well, it essentially says the same thing as the first statement, but just for elements in the left set. For example, elements in the left set can be expressed as a times I and a times j, where I and j are greater than or equal to 1 and less than p. And so it essentially says if a times I is congruent to a times j mod p, or any elements in the left set are congruent, then those elements are equal to each other, implying, as in the previous case, that elements in the left set are all distinct. Now, we can't just assume these. Mathematics is all about proving, so let's prove these statements. Okay, let's take the first statement. So I is congruent to j mod p, so therefore I minus j is congruent to 0, which it can be congruent to p, 2p, 3p, minus p, minus 2p, minus 3p, and in general an integral multiple of p. So first let's start by assuming that I is greater than or equal to j, which is a very useful tool because we're essentially bounding these two integers, but it always holds true. We can pick the I in such that manner. Okay, so remember, we've chosen I and j to be greater than or equal to 1 and less than p, which implies, given with the fact that I is greater than or equal to j, that I minus j is greater than or equal to 0 and less than p minus 1, which becomes a very important bound for the difference I minus j. And now note that I minus j cannot equal an integral multiple of p that is non-zero. And if I minus j equals an integral multiple of p, then that's when it's congruent to 0 mod p. But since I minus j is greater than or equal to 0 and less than p minus 1, the only integral multiple of p is 0. So therefore, I minus j must be equal to 0, and that's the only value for I and j that satisfies the congruence. And therefore, I is equal to j itself, which proves the claim. And as we talked about before, this means that all the elements are distinct modulo p. Okay, so let's return to the second statement. So, as usual, we subtract on both sides, and now we can factor out an a. But remember that since p did not divide a, we chose a that way, then a cannot be congruent to 0 mod p. And thus, a cannot be the factor that turns a times I minus j to be 0 mod p. And so therefore, I minus j has to be congruent to 0 mod p. And as we saw before, this implies that I is equal to j, proving the claim. Okay, and similarly, this means for elements in the left set that all of them are distinct modulo p, as we talked about before. Okay, so now returning, we need just one more important piece of information, and it's in modulo p. In modulo p, there's at most p distinct values, namely the ones you see on the screen. These are essentially 0 plus an integral multiple of p, 1 plus an integral multiple of p, 2 plus an integral multiple of p, and so on up to p minus 1 plus an integral multiple of p, where, as I say integral multiple, that just means an integer multiple, and so all the coefficients m1 up to mp are integers. And we can intuitively see why if we take this set modulo p, essentially reducing the integer multiples of p, and we get this set. Now, let's say we want to extend this set to the right, so we add p to the set. However, p is congruent to 0 mod p, and so that just loops to the left end of the set. But also, if we go to the left, including -1 in the set, well, -1 is congruent to p minus 1 mod p, and so it essentially loops to the right side of the set, and thus that is the maximum number, namely p elements, that can be distinct modulo p. So, we have proven that there are at most p distinct values modulo p, and we can use that in our argument. So let's return to our sets. But notice how our sets only have p minus 1 elements each, but they're both missing 0, so let's add 0 to create a total of p elements in each set. And notice that when we add 0 to both of these sets, these new sets are still distinct modulo p, because we proved that the original sets were distinct, and since no elements in the original sets were congruent to 0 mod p, when we add 0, there's no overlap in the integer values modulo p, and thus both of these new sets are still distinct. And now each set has p integer values that are all distinct, meaning each set has reached the maximum p number of distinct integer values modulo p. Okay, so something very interesting can be deduced from that conclusion, and that is, since both sets have the maximum number of distinct integer values modulo p, then both sets must contain the exact same values. Because you don't know which value corresponds to which other, but you know that each of the sets just contains all of the possible distinct integers modulo p. Now that we know that these two sets contain the exact same elements, we can map the elements in the left set to the elements in the right set, forming a one-to-one correspondence, since each set has the exact same values. Now, we want to deal with our original sets. These new sets contain 0. But notice, since 0 maps to 0, meaning 0 is congruent to 0 mod p, meaning they have the same value, then if we remove 0 from both sets, there's still a one-to-one correspondence between the remaining sets. And that is what we wanted. Okay, let's see an example with p is equal to 7 and a is equal to 4. And let's show there's a one-to-one correspondence between these sets. So 0 maps to 0, 1 maps to 8, and so on. And notice that although this is with sets both containing 0, since 0 always maps to 0, we can remove 0 from both sets and still maintain the one-to-one correspondence, which is why our original sets have a one-to-one correspondence without having zeros. So let's return to our original case. Now, because there is a one-to-one correspondence between these two sets, I claim that this following congruence should hold. And the reason for that is because there's this one-to-one correspondence, meaning that all the elements in the left set must be congruent to all the elements in the right set modulo p. Then when we take the product of all the elements in the left set, that must be congruent to the product of all the elements in the right set, because simply all the elements in the left set are congruent to all the elements in the right set. And since we are taking a product of all the elements in the left set, that must be congruent to all the elements in the right set, modulo p. And notice now, on the left side we have 1 times 2 times 3 ... up to p minus 1. That's p minus 1 factorial. And on the right side, well, first of all, we have p minus 1 a's multiplied together. So that's a to the power of p minus 1. But we also have p minus 1 factorial because we have 1 times 2 times 3 ... up to p minus 1. And so on the right side of the congruence, we have p minus 1 factorial times a to the power of p minus 1. So we can rewrite the congruence, subtract on both sides, and factor. First, note that p minus 1 factorial cannot be congruent to 0 mod p, And this is because all the integers from 1 to p minus 1 are coprime to p, and thus when you multiply them, that result, which is p minus 1 factorial, is still coprime to p. And since p minus 1 factorial is coprime to p, it cannot contain any factors of p, and therefore cannot be a multiple of p, meaning it cannot be 0 modulo p. Thus, for the bottom congruence to hold, 1 minus a to the p minus 1 must be the one that's congruent to 0 mod p. And therefore, 1 is congruent to a to the p minus 1 mod p, or a to the p minus 1 is congruent to 1 mod p, Fermat's little theorem.